I'm just starting. We are now reviewing the old topics. So this is a typical step down type of application. When you put the switch on, the current is going to flow through that network, and then when you put it off, since you have already stored energy here, current is going to flow through that network. We have already given the equations of those. It's here. The first part, switch on, and the second part, through the feedback diode, or sometimes, quite often, it's called freewheeling diode, current flows. We know how to derive those equations. I several times have driven those equations. These are the equations we can calculate. And also there are two cases. One of them is continuous current operation. The other one is discontinuous current operation. For discontinuous current operation, of course, the value of inductance is low and the voltage here is high. Then that might be a battery as well, or anything. In that case, current is going to be discontinuous. For both cases, we have driven the equations you already know, and also you know for continuous current mode the minimum current and maximum current calculations, and you know what Z here is T over tau actually. Z here, the simplest term, Z here was T over tau. Tau is L over R, time constant. Okay. And delta I could be calculated, this one, and delta I max is occurred for K equal 0.5. And this equation, the red one, the approximation, is useful. It reflects how important to increase the inductance value, which means obviously volume and money cost, and how good increasing the frequency would be in order to reduce the current variations. And the value of X is also definitive. If E is high, then you have a limit here. So E over Vs should be smaller than this for the continuous current operation. This is what we have already done before. And the RMS current could be calculated. Step up action is obvious that when you turn this switch on, then you are storing energy in your inductance, and then when you put it off, similar to the, assume that a bicycle wheel is rotated, and then when you put it, then it moves. You see, if you lift the bicycle and operate the wheel run the wheel with a higher speed, and if you leave it, then it moves. Similar, that voltage plus this voltage, of course, we are now storing energy, and then when you put it off, the current is going to flow through the right hand side of the equation of the system, and this voltage and the voltage of this one becomes higher. So the voltage here supports this voltage, supply voltage, and produce a higher voltage. This is called step-up action. And in contrast to VA output, or VO, is equal 1 over 1 minus K times Vs. K is turn on and turn off time of the switch. That is what step-up action is all about. and we have driven those equations. You can see that equation here. I just remind you what we have done so far and the operational principles we have already derived. For continuous current, we have driven the equations as well. That is the case. You can see that the first case switch is on and these equations are valid. If that one is off, then we end up with the other equations, the equations relevant to the second circuit. Energy is going to the right hand side of the system. Now that one is interesting here, that it's actually step up, but there is a resistance. Resistance is added to the voltage or the battery. Okay, and when you put it on, then current is going to flow, and then when you put it off, this switch, then current is going to flow continuous to the voltage, and it's going to produce a voltage higher than this one. Mode 1, that's the one, switch is on. Mode 2 is you already send the current to the supply. Of course, now you are capable to send the current, produce a voltage which is higher than you are. It's that configuration. That configuration is used for electric vehicles where the battery voltage actually lower than the DC bus voltage for electric vehicles. And these are the equations, the maximum, minimum, and maximum current equations derived. As far as, and also this is the ripple one. As far as I can remember, last week we have reached to that point, and we have defined the 4-quadrant operation. Now, be careful. That one, VL here, biraz büyüteyim, is not the inductance voltage. It's the voltage of the load, okay? And the IL is the current of the load, and the system is actually 4-quadrant operation. System is actually something like this. One switch here, another switch there, one switch here, and another switch here. These are controllable switches. So that is the structure, plus and minus source. But these switches have parallel diodes. In opposite direction. Switches positive directions are shown, but the diode direction is opposite to this. But load is located, onu başka renkle göstereceğim. Siyahla göstereyim. Load is located here. In general form, load might be a resistance, might be an inductance, might be a voltage source or back EMF. That might be an electric machine as well. This might be an electric machine model as well. So that point A and that point B is important. So R, L, and E. Okay. Now I'm going to start in summary. Şuna bir diyelim. that one 1, that one 3, that one 4, that one 2. Sırayı öyle mi kullanmış? Hemen bir kontrol edeceğim. Dört, tamam, 4. Şimdi çocuklar bu modeli aklınızdan çıkarmayın. Yani never forget that model. Hatta biraz yürüyeyim ileriye, bakın. Four quadrant, burayı çok iyi anlayacaksınız. Çok üzerinde düşündüm, en iyi böyle anlatılır diye. That is the four quadrant system. You can see that this point here is A, and this point is here is B, and this is the load terminals. Now if you run S1 switch on and S2 switch on, then current is going to flow like this, flow like that, and it's going to rise. But if you put S1 off but keep S2 on, what's going to happen? Current is flowing in this direction. Current is going to continue like this. So on, off, on, off. This is buck operation. But for the boost operation, of course, you are now going to, this one put it off, that one put it off, S1 put it off, and then you already store energy in your system, either electric motor, mainly electric motor, but it might be also a battery or something like this. But plus point here, never forget that the plus point here in the, that is the plus. That is the plus. So actually what happens, that is the plus. So actually what happens here, current is going to leave the source and put S4 on, and then through diode, current is going to flow like this. You are actually storing, current is flowing like this, and you are actually storing energy in your inductance. When you put this switch off, what's going to happen? Stored energy goes back to your source through D1 and D2. So that kind of current you can flow. So on and off, you can run the system in opposite direction as well. That mode, current is negative. For this current is a reference one. That is the model, don't forget. And be sure that that plus here is not always valid. Bakın siliyorum o şimdi. Bunun hepsini uzun uzun anlatacağım. Sadece özet başlatıyorum. Bir form tutun istiyorum. Şimdi I have a question. I put S3 and S4 on. What's going to happen? Önce onu düşün. Biraz evvel, just a minute ago, I said S1 and S2 were on. And the current was, if S1 and S2 on, current was flowing like this through that network. But now I'm saying that if I put S3 and instead of S1 and S2, if I put S3 and S4 on, what's going to happen? Think about this. It's obvious. Current is going to come, flow. No, I put S3 and S4 on. current is going to flow. I put S3, S4 on. Current is going to flow like this. If it's going to flow, and this if that one is an electric motor, electric motor E back has got a different, so it's entering part. If here your voltage is negative between terminals of let's say that point is A. If you stand right now, I'm going to explain it properly. Minus multiplication, power is positive. That's right. If you can't hear me, you just wait, since I have seen that probably many people now entered the classroom. I'm not talking about you, but also other classrooms in the university. So it seems that the quality of the broadcasting, let's say, is very low. Red light appeared. Okay, I'm going to start from very beginning. In order to improve the quality of the teaching, I disconnect my picture, so you can probably hear and see the course material better. Okay. Now that's the brief starting point. So these are the quadrants. If current is positive and if current is positive and the voltage of the load terminals are positive, it's the first quadrant. Power is positive. If current is negative, here in third quadrant, if current is negative and the voltage is negative, product negative multiply negative is power is positive. So this reflects the reverse direction of the electric motor. Okay, so this one, the first quadrant, reflects the motoring case in positive rotation. Third quadrant is motoring but in reverse rotation. Second quadrant is the motor is rotating in the positive direction, therefore voltage is positive, Voltage means also back EMF also reflects that one, but current is negative. So it's actually a braking part. So power direction is negative actually. So you are braking your electric motor. And the third part is also your current is positive, but in this case your voltage is negative. Then this is also braking since power is negative. But power is negative means your system is rotating in opposite direction. So positive motoring 1, negative motoring 3, positive braking 2, and positive, sorry, uh, that's right, negative braking is 4 quadrant. These are the quadrants. Now we are going to discuss. Follow me. If you don't understand, just raise your hand and ask the question, open your microphone and say something. You can interrupt me, all right? You already know what step down is all about. You already know what step up is all about. Now consider the second quadrant operation. I don't like this figure. I strongly criticize Mohammed since that figure is already explaining things. This is the some part of the uh, four quadrant operation. So first quadrant, what's happening? I put S1 on. There is no S2 here, so assume that S2 is on. What's going to happen here? Current is going to flow. That point is A, and that point, onları işaretleyeceğim çocuklar. Sonradan kafanız karışmasın diye bunları işaretleyeceğim. That point her zaman AB'yi kullanacağım. That point is A, and that point, buraya taşıyorum bunu kafanız karışmasın diye. B. So that's AB. Okay. Tabii ben Muhammed'in yerinde olsaydım kitabıma böyle koyardım, bakın yok yükü. Böyle koyardım. Buraya A derdim. Buraya B derdim. Bunu buradan gönderirdim. Bunu da buradan böyle kapatırdım. Yüke bağlardım. Anladınız mı? A'yı B'yi. Yani bu şu düşey koyması for vertical representation is misleading for the students. That is actually part of this one. Bakın bunun aynısı. Inductance, resistance, and back EMF, electric machine. And here we have another switch, but this switch is not shown here. So gelelim first quadrant'a, biz işimize bakalım. Artık hepsini biliyoruz denklemlerini bunların. Şunu sileyim. Hepsini bir sileyim, temizleyeyim. Evet. Şu A'ya B'ye koyacağım ama. So VAB is actually VL, load. Unutmayın. Inductance gerilimi değil. Bakın VL demiş. Görüyor musunuz? VL'i burada göstermiş. Tamam. Şimdi ne oluyor burada? What's going to happen? I put it as S1 on. So current, bu mavi okları ben koydum size yardım etsin diye. S1 current flows through that one, through inductance and the back EMF, or if you have a capacitor that might, or if you have a battery, that also might be. Then current flows like this. So what's going to happen? It's a buck converter type, or it's a, I'm sorry, it's a reduced step down type of operation. Therefore, current is going to, you are going to supply energy from your battery to the system, okay? And then you are going to, when you put it off, current is going to rise, by the way. Bakayım ne var şekil. Ha, evet, denklemlerim var. Denklemlerim var. O denklemlere girmeden evvel iyice bir anlaşalım. So that is the case, okay? That is the case. When you put this switch off, what's going to happen? Since energy is stored here, then current is going to flow. Current is going to flow through that network. So you have already stored energy. So S1 and on and off, on and off. So what's going to happen actually? Evet, orada da denklemlerimi yazmışım. Şimdi bir saniye. Current is going to rise. Here, current is connected to VAB. Tamam. Şimdi denklemlerine bakacağız. Biraz büyüteceğim. This is the first quadrant. Şimdi loop equation'ı yazıyorum. Loop equation'ı beraber gidelim buradan. Bakın yürüyorum loop'tan. Minus Vs plus delta V S1 plus L di dt plus Ri plus E. That's all. O denklemi şimdi hemen görelim. Minus Vs delta Vs1 L di dt plus Ri plus E is equal to 0. So Vs is equal to, neglecting the voltage drop of the switches, LRE equation. We already derived those equations. Current is equal. So we have two sources. One of them is Vs, the other one is E. So it said both of them are DC. So Vs minus E over V, I'm sorry, Vs over E over R görebiliyorsunuz değil mi? You can't see that one, can you? Biraz daha büyütürsem daha mı net? Evet. Vs minus E over R plus K. This is a steady state solution. And this one is transient solution. Current is rising, but we assume that we are in the continuous current mode. Therefore, time equals 0. Current is equal I1. Generally, when I was teaching at Istanbul Technical University or even in classroom, I use I minimum and I maximum. But I believe if you read the material, Mohammed Rashid, he prefers I1 and I2. That's why I use I1 and I2. So this one is I minimum, this one is I maximum. But current is continuous. Don't worry. Don't consider that one. Evet, bir takım el işaretleri yaptığımı fark ettim. Beni görmenizde yarar var. Zaman zaman. Evet, toparlıyorum. Şimdi current is rising, but initial current is I1. Therefore, time equals 0. This term becomes 1. That one, exponential terms. So initial value is equal exponential terms. So initial value is equal I1. I1 is equal Vs minus E over R. So I calculate K from here. K is equal I1 minus Vs minus E over R. So if you put it there, if you put it here, okay, I is equal Vs minus E bracket I1 minus Vs minus E over R. Therefore, the final equation would be IT, time function actually, this one, I1, Vs minus E over R, 1 minus E to T over tau. What is tau here? L over R, L bölü R in Turkish, plus I1. So that is one equation. So it's rising. How could I find, if I know I1, how could I find I2? I have a question. Quiz. How could I find I2? Time T on. If time is equal T on, that means T is equal KT, then current is going to be I2. So if you consider that one, T equal T1, which is equal T on. Kitapta T1 diye gösteriyor. Muhammed Rashid reflects that one as T on, T1. But I prefer to write here T on, which is equal KT. So if you replace time is equal KT, then you are going to obtain I2 here. I1 and I2. So this is the first equation between I1 and I2. Okay? Is it all right so far? So we studied that part. But now we are going to turn this switch off. What's going to happen? Then because of the stored energy, current is going to flow like this. But the current is equal I2. Never forget that. Now current is in the maximum. Then we come to this case. We put S1 off. However, D4 is inherently, although I put it here D4 on, not necessarily. You shouldn't write that one. I just wanted to remind you D4 on. So the current is going to flow like this. Of course, stored energy is going to be reduced and the current slope is going to be negative. Current slope is going to be negative. You can see that current slope is going to be negative. But the duration of this one is equal 1 minus k times t. That one. This one is kt. That one is 1 minus kt. So it's off time actually. Let's continue to write the differential equation for that case. I write L di dt plus R plus E, neglecting the voltage drop, is equal to 0. Tamam mı? Bunları çocuklar artık, yani bunlar peynir ekmek size. Bakın hemen yazıyorum şuraya. 5 punto olmaz. Küçülelim. 1 punto yazayım, bakayım nasıl olacak. L di dt plus Ri plus E is equal to 0. E neye eşit? Minus E over R plus, bu sefer time'ı kaydıracağım için Chi prime dedim. Orta. Time prime is equal 0. I is equal kaç? Ne? Söyleyin. Initial value of this case. This current. I'm writing the equation for this part. Current is equal I2. I max, in other words. I equal I max. Buradan arka sayfaya gidiyoruz. Evet. S1 of stored energy in inductance and D4 inherently on loop equation, which I have already written, LDI dt prime. I assume that starting point is equal 0. That's why. In order to employ the and differential equation, and the solution is this, which I have already derived that one. Sorry. If you can't see the cursor, urge me please. I is equal minus E over R plus K E T over tau, T prime of course. T prime is 0, current is equal maximum. And then you obtain the K prime is equal I2 plus E over R. So if you replace it here, this equation, this is the general equation. The K prime we already obtained here, put it here, minus E over R plus I2 plus E over R times E to power minus T over tau. Then this differential equation you obtain. Okay. Current equation of course has got a negative slope. Nereden biliyorum? Tabii buradan da matematik, I can see mathematically, and also I can, that is the slope is negative, reducing of course. Then this is the second equation. If I put time prime is equal 1 minus kt, what am I going to find? In that case, I'm going to find I1, I minimum. The second equation is this one, that one. So I1 is equal to E over, of course, I put T prime is equal 1 minus K over T instead of. So here also, instead of T prime, we put 1 minus KT. So we obtain the second current. The first current, the first equation here, I1, sorry, I2. The second equation is here. So in that case, I go back to Mohammed. These are the boundary conditions. Derive time domain equation and obtain the following results. Bakın homework gibi bir şey yazmışım buraya. Ben yaptım ama sizin için. I1 and I2 minimum and maximum current could be calculated. Okay? Evet. Buraya kadar anladık mı? Did you understand that one? It's actually step down action so far. Step down action. Now the first quadrant is all right. So far, bir dakika ileri gidecektim. So far, we have completed the first quadrant operation. That's right. The first quadrant operation we have completed. S1 modulating, S2 continuously on. Actually, S2 here, although it's not shown by Ahmed, but S2 is continuously on. And S2 and D4 are operating. So When the switch S1 is on, current is flowing like this, and then if you put it off, current is going to flow through that one. Then when you put it on, current is going to flow like that. So from source you send the current is rising, and current is then dropping, and we already know the maximum and minimum current, and we already know the time domain equations. It's the first quadrant operation. Now for the second quadrant operation, S4 is going to on. S4. So the other switches, control switches are off, S4 on. Who is going to describe what's going to happen here? You already store your electric motor is rotating, and the plus point here, the reference plus is here. I put S4 on. Who is going to describe it to me? Haydi. Come on. Bakın ne olduğunu söyleyeyim size ya. Çocuklar yapmayın ha. Bakın ikinci kuadran. Burada kaynak var. Akım buradan çıkacak. Bu switch on. Buradan geçecek. Böyle ki devam edecek. It's going to complete this network. That's all. So current is going to flow like this one. Since we have already stored energy here, a voltage source here, and voltage source reference daima pozitiften çıkar. The current leaves the positive point, and the current and this switch is on, and the current is going to flow like this. Current is in negative direction. Since this point is A, that point is here, that point is here, A. Kırmızıymış ya. Siyah istiyordu. That point is A, that point is B. Ama şuraya yazayım. VAB is equal VL. Şu VL. VL VL is positive still, since you have a source here and that point is connected, and the positive point A is positive, B is negative. Therefore, VAB is positive. So voltage is positive, but current is negative. Current reference current direction is this one. Current is negative. Current is flowing in the red line. Then when you put it off, what's going to happen if you put S4 off? Current is going to flow, since you cannot change the current direction. Then current is going to flow to, onu da dash nokta nokta göstereyim. Şu S1 on olsun. Yazıyorum. Şimdi ayrı şekilde anlatacağım ama bu şekil çok daha öğretici. S başlanmadan Kırmızıyla yazdığımıza göre kırmızıyla yazacağız. S for on. Şimdi Blue'yla da S for off'u yapacağım. S for off. Since you have stored energy here, current is going to flow D1 and D2. Burada ne yazıyor? Bakın. Büyütüyorum. What's written here? S4 is modulating. Modulating means sometime on, sometime off. And D2 is a partner. Red color. That one. And the blue one, D1, D2. So stored energy goes back to your supply. Of course, current is going to, in red one, current is going to rise. But if you put it off, say S4, then you are going to send some of the energy back to your system. It's a kind of step-up action, by the way, since this voltage actually is lower than Vs. However, with the support of the voltage here, the current is going to continue and connect it to the higher voltage value. Step-up action occurs. Okay. Şimdi denklemlerini konuşacağız. Buraya kadar anladık mı? Umarım. Fazla bir sessizlik hakim. Biraz şey yaptım bu işten. Şimdi baştan alıyorum. Bu bak. Tamam mı? That's step down. That one is step down. First quadrant. That one is the equations of this one. And this one is again first quadrant. So current is rising. Then current is circulating, reducing. Then again rising, on and off, on and off. It's the first quadrant. Okay? And the first quadrant equations it's not second quadrant. It's still first quadrant. Control switch on and control switch off. This one is off part. And the I1 and I2 could be calculated by this one. That was the case. Bu second quadrant değil benim derdim. Evet neyse karışmasın. Şimdi second quadrant'a geçeceğim. First quadrant bitmişti. Şimdi second quadrant'ı Muhammed'in anlattığı tarzda başlıyorum. Şimdi what we do now, put S4 on and current is flowing like this because of the source here. Bu artıyı da ben koydum. Kendi zahmet edip koymamış. Yanlış. Yani artıdan çıkar. Current leaves the positive point of the whatever it is, battery or the voltage source. And bak burada artı var. And also current flows like this and rising. The equations will be, then when you put it off, then of course the current is going to flow through that line. Since you have already stored energy in your inductance, you cannot, without changing the direction of without taking all the stored energy back from your inductance, you cannot change the direction of the current. Be careful. while current is here, so that means current is going to flow in that direction anyway. So if you put this switch on, stored energy is going to flow through D1. That's the way. Through D1. Zannedersem clear. Şimdi bunun denklemini yazın desem, you already know how to step up action is all about. You can write that one. Ben yazmadım bir daha. Ama yazabilirsiniz yani. Bakın küçük bir prova yapalım. Şuraya şeyi sığdırmaya çalışayım. Önce Kirchhoff Voltage Law. Şuradan başlıyorum. Loop'u şuradan çeviriyorum. Minus E plus Ri plus LDI dt plus delta V voltage drop of S4. Bu S4'u niye yazıyorum? That reminds me the direction of the network is equal to 0. So actually I, which is in the reverse direction, E over R plus, hadi hep K kullanmayayım, kafanız karışmasın. Bu sefer de A kullanayım. Time equals zero. I is equal I1. Continuous current operation. Therefore, A is equal. Şimdi bakın buraya bunları tamamen ters yönlü yalnız. Don't forget that current is in negative direction. Don't forget that. Yani bu yönde. Referansın tersi. A is equal since it's continuous. Bir dakika, I minimum yazdım ya. Alışkanlık, hep I minimum yazarım. I1. I1. So buradan current is equal to E over R parantez 1 minus E T T over tau plus A'yı yerine koydum. Bir de I1 var burada. I1 çarpı I'm sorry, into Turkish I1 T over tau. That's the equation. So what happens if I put hadi Eflatun'la yazayım, dikkatinizi çeksin. If time equal kt, I becomes I2, I max. But current is negative direction, don't forget. So you already obtained the Imax. For the next part, for this part, then you are going to continue. Yazıyorum denklemi gene. Minus E, Kirchhoff law, plus Ri, plus L di dt, plus delta V d1, plus Vs. Burada bir tane diyot kullanmış. Aslında for quadrant'ta iki tane var ama tamam, bu kalsın böyle. Eşittir zero. Buradan we neglect the voltage drop. Vs E minus Vs, Vs pozitif kalsın, bir dakika. L di dt plus Ri is equal to plus Ri is equal to minus Vs plus E. O da eşittir. Eksi parantez Vs minus E. Hangisini tutsam acaba? Kalsın böyle ya. Karıştırmayayım kafanızı. Böyle kalsın. Buradan current I is equal to minus Vs plus E over R times, buna B diyorum bu sefer, time prime yaptım. Hadi yok, bir öncekinde aynı olsun. K'ya K üssü demiştik. da aynı olsun. Constant. Bu sefer A prime diyorum. Şimdi buraya bir initial value yazayım. Time prime is equal to 0. Time actually, evet, burada problem çıktı. Time prime 0 iken time kim yazdıracak? Yazamıyorum. Actual time kaç? Time shift yapıyorum aslında. Zaman kaydırması yapıyorum. Yani bakın burada şu zamana 0 derseniz, if you assume that this time is equal to 0, actually actual time is equal kt. Similar behavior we do that. Similar manner. Time prime 0 dediğinde time is equal actually kt. Evet, bunu çözeceksiniz. So time prime is equal to 0. I nedir i'ın değeri? Maksimum. Bir öncekinin son değeri. Bunun son değeri. If put time equal kt here, you obtain the I2. Okay. So bunun da initial value'sudur. Buradan I1 and I2 obtained. Evet, yoruldunuz. Ben de yoruldum. Bir ara vereceğim. Bakayım ne yapmışım. Evet, for kadrana gelmiş sıra. Saat şu anda, benim saatim 10 geçiyor. 15 dakika ara veriyorum. 10:40, 10:25. Break. Okay, see you. Hello again. Now, I'm going to make a brief reminder of those 4-quadrant operation. Please follow me. Now, for the first quadrant, we put S1 and S2 on, and one of them still on, S2 is remaining on, and S1 is modulating. Modulating means turning on, turning off, turning on, turning off. If it is turning on, current is going to flow like this. If it is turning off, then since energy is stored here, current is going to continue through that line and through D2. Sorry, uh, S1 is off and current is going to flow. S2 is on through S2 to D4. On, off. For on, rising, off is reducing, but it's continuous. So it's, if it is an electric motor, that electric motor is this is a model of electric motor, you can see that. Then this electric motor is rotating in positive direction, motoring. So I just explain it in the point of view of electric motors. So this one, electric machine. Okay. For electric machine, that is A and that is B. So that one is VAB. Quadrant 1 is motoring. That one is the second one, also the current. That current AB. So that one is motoring. For quadrant 1. For quadrant 3, then in that case, S1, I'm sorry, S3, follow my cursor please. S3 and S4 are on, current is flowing in negative direction, voltage is reversed. I repeat, we are in the recording, so while you are listening, if you listen again, you might be careful. So recording, the voltage is reversed, and the voltage becomes different, of course, in the opposite, and the current flows from B. Voltage is negative and current is negative, therefore power is also motoring here. The third quadrant is also motoring. Switches, obviously S3 is modulating, however S4 is continuous. If you put S3 off while current is flowing in this direction, then it's going to rotate through D4. Sorry, D2. Through D2. Current is flowing like this. On the other hand, if you run the system in somehow regenerative mode, since your machine is rotating, your machine is producing E, electric machine here, E, speed of the electric machine is omega m, and the design constant, and torque of the electric machine is K times current. So if current rotates, current reversed, torque reversed. And also if E reversed or speed reversed, E also is reversed. So for positive motoring, of course, positive motoring in omega, that one is omega mechanical is positive. Here omega mechanical is negative. So speed is negative. But speed is negative. But torque is negative too. Torque is negative too. So product of those is, but however, torque is positive here. So positive direction and positive rotation, negative torque and negative direction. So rotating in opposite direction. Both are motoring. These are regenerative braking case where you can change the direction of current for this case. While current is positive here, so torque is positive. I'm sorry. While omega is positive, so rotation is positive. But in the meantime, you are changing the current direction. Torque is negative. Renk değiştirdim mi? Evet. Torque is negative here, but speed is positive. Speed is positive. For this case, however, motor is rotating in different direction. Current is positive. If current is positive, torque is positive. Torque is positive, but omega mechanical. Ben bu bilgisayardan habire işime karışıyor. Omega mechanical is negative. For four quadrant operation, if you manage to give a positive voltage, positive current, then your system is going to rotate in positive direction. And if you manage to give negative voltage and negative current, your system is going to rotate in negative direction. However, for braking, you are either produce a negative current while it's rotating in positive direction, since voltage is not reversed actually, voltage is positive. VAB is approximately representing the E, inner voltage, which is proportional with the speed. You can see that speed is defined by VAB actually, and the current direction. Is it now clear? I start from very beginning. If you consider that one is also an electric motor, which we represent the electric motor with inductance, resistance, and the back EMF or induced voltage. If If you rotate in a positive direction, that means you are in the supplying from V, you are giving VAB positive, and the current positive, you can see the current direction here, IL. Then your E is positive and torque is positive, since current is positive and speed is positive. That is motoring. However, if you run S3 and S4 pair in the third quadrant, you are actually giving a negative voltage to this system. That E is also reversed, and also current direction is reversed. Then you are again giving input power to your electric motor, but in reverse direction. It is motoring. Torque is negative, and also speed is negative. It's motoring. However, while it's rotating in reverse direction, if you use the four quadrant operation, where you can modulating S3, however, and together with D4, but then when you put it off, then modulating means sometimes it's on, sometimes it's off. Then D3 and D4 is going to, both are going to operate and send energy back. So this is also braking, regenerative braking case. However, speed is still negative direction, but you give a positive torque. So reverse torque. Bu çocuklar, bunlar electric vehicle'da might be used for regenerative braking cases in electric vehicle. Probably in the future, some of you are going to work in the electric vehicle part, since the electric vehicle market is expanding. Therefore, we also have some. We also have a factory in Turkey now, and there are other, productions are getting in. Yet, I think Renault is now preparing itself, and also Toyota is producing long time electric motor driven hybrid electric vehicles. Therefore, this is the basic principles. I hope you did understand that topic. That's, for example, third quadrant operation they described. They simply, Mohammed made it simple. That is not actual case, however. You can see that there is a switch here, and as long as you switch that one on, and the voltage is actually not like this, voltage is covering all of them. But that's not wrong. This picture is not wrong. Third quadrant operation, you are putting the S3 on, and the current is flowing like this, and then the voltage source reversed. You can see that, since current, göstermişim bakın, current direction enters this part. Of course, this reference current is still remain there, but actual current is negative. And however, this voltage is also changes direction, and therefore is the third quadrant motoring operation. Current is negative and voltage is reversed with respect to the one before, and then it's motoring. And also, while you are storing energy in your inductance, you cannot reverse the current. If you put this switch off, current is going to flow like this. So it's going to, of course, current is going to reduce, but it's going to freewheeling. It's rotating in a freewheeling part. For this example, however, this third quadrant operation, we are actually storing energy in our inductance and give that energy back to our supply. This is more realistic. He made it simple for teaching purposes for this one. That's right. I think it's enough. So how could you control your? You remember we produce a trapezoidal waveform. So we measure the output voltage. If we compare it with the reference actual what we wish, so the difference is between the reference and the actual output is error. We amplify that error and we produce the control signal, and these are the um, trapezoidal waveform. So we control uh, compare with trapezoidal, and we send the gate signal to our DC chopper. This is the basic principle of the DC chopper. Now we are going to look at the. It's going to be very simple for you, by the way. Uh, it's going to be very simple since you already learned all the system equations. Buck converter is actually step down. This one is actually step down. It's step down converter. Önce şu şeye bir bakalım. Perhaps you know that final exam is going to be face to face. So you must be preparing yourself for the final exam. Although I couldn't look at your midterm exams, but I know from quiz answers, I feel that you need extra work in order to pass this course. Okay. Now that is easy. That one is easy. All you have to do, if you see a network like this, always consider that this capacitance is trying to keep the voltage constant, reduce the voltage variations parallel to the load generally. And this inductance is generally in series line. It is going to be the purpose of the inductance is to keep the current, reduce the current fluctuations. Okay. And if you look at the main switch, you are going to see that it's either on or off. Let's put it on now. If that switch is on, then what's going to happen here? Switch is on. Current, we have a DC source here. Then current is going to flow. The current here is going to flow to the load, through inductance. Some of them also charge the battery. I'm sorry, charge the capacitor. That's all. Then what's going to happen? Current is going to rise. Is T on? Switch is on. You can see that. It is on. In the meantime, current is going to rise. We are going to see the equations anyway. We assume that it is continuous current mode. Inductance current, by the way, this time. IL is inductance current. Inductance current is going to rise. And also supply current is exactly the same as this one. It's going to rise linearly. However, the capacitor current also is going to rise, but the current load current, that current is a load current. IA is the load current. And the capacitor current, the difference between those is depends. This one, for example, you can see that the current from that part, the capacitor current is going to rise, and it's going to be peak at when the time comes at equal k to t. That means on time. T1, if you follow me carefully, T1 is a on time. T1 is a on time, and T2 is the off time. But in our terms, since K is the duty cycle here, if you write duty cycle, so that means this duration T1 is equal KT. T1 is equal to KT, and also T2, which is equal T minus T1. T2 here, you can see that switch is off. Then T2 1 minus K time T. Okay, so these are the equations we have. Bayağı bir boşluk varmış yanda. Evet. So you can see that during that time, by the way, since we are charging capacitor, our capacitor voltage, or rather output voltage, is also become undulating. When the time comes and we put the switch off, then of course no current is going to flow. So when you put this switch off, en yukarı gidiyorum. When you put this switch off, current is going to flow through that network. Through this network, since we have already stored energy in your inductance. But also, the capacitor is also supplying current. Of course, this is the reference direction, by the way. It's shown here. You can see that that one is a reference direction. Now the capacitor current, then immediately, of course, output voltage, supply voltage is not going to supply anymore. Neredeyiz? Buradayız. You can see that this is the current. Gene 0,1'e alalım bunu. Kalınlığını. İnceltelim. Ya da dursun ya. Tamam. Current is going to flow. Like this. Therefore, supply so that kind of inductance current is going to reduce linearly, and also supply is not giving current to the system. In the meantime, the capacitor current is going to be reduced. And also capacitor voltage continues to fluctuate. However, finally, that one, onu başka bir renkle göstereyim. We assume that our output current is flat. Tamam. Şimdi baştan alıyorum. For initially we put switch on and the blue color direction occurs. Battery is charged, therefore battery current is rising, and also battery voltage is also rising. However, the battery or output voltage fluctuates, but and the supply of the supply system, your supply system gives that current, that blue current, and this is the capacitor current. When you put the switch off, then some of the current comes from battery to the load, and some comes from the stored energy inductance. They share it. Current, of course, has got a negative slope with from maximum to minimum, and in the meantime, no supply current from source. However, the inductance current is also similar pattern, and the voltage of which I'm going to show that one to you, but the load always has a constant current. So that one is AIA. Onu göstereyim. Şekil tamamlanmış olsun. Çalışırken belki faydası olur. Load current is assumed to be flat. Şimdi gelelim denklemlere çocuklar. Eğer if you understand that one, turn on, buck is a step down actually, and turn off. You already know step down operation. Therefore, Mohammed directly writes those equations, and they say output is equal KVS and delta I is equal to this. I was not happy about that one. Then I add that one to you. I don't know whether you can see this. Inductance voltage is equal LDI dt is general rule. And we all assume that current is rising linearly from I1 to I2. So the difference between supply and the load is equal L di dt. Di is equal delta I is I2 minus I1 over T1. Gidiyorum şekle. Bakın. Buradaki süre T1. Buradaki süre T1 and current is rising between I2 and I1. So I2 minus I1 is delta I divided by T1 is LDI dt actually. Eminim bundan memnunsunuz. Buradan T1'ı çekiyoruz. We take T1 is delta I times L over Vs minus Va. Va output. Tamam mı? Fakat in the second part, which I draw with red, the current falls from I2 to I1 in time T2. T2 time hangisiydi? Sorry. That is T2 time. Büyütüyorum. That is time T2. That means 1 minus KT. So when the switch off, control switch off, and the system supplies energy stored in inductance and stored in the capacitor, the red lines, red color. For this case, only voltage source is equal VA, and if you write the Kirchhoff voltage law, minus VA is equal minus L di dt. Time is this time T2. Therefore, T2 is calculated di L over VA. So delta I is equal to first equation here. You can see that delta I is equal Vs minus Va times the first equation here. Delta I is equal to Vs minus Va times T1 divided by L. İniyorum aşağıya. Vs minus Va L. And the another one here, delta I is equal V output T2, that equation. You get it with L. Şimdi iki tane equation var. T1 and T2 var burada. Devam ediyorum. T1 is KT'dir. You remember that. T2 is 1 minus KT'dir. Therefore, VA denklemde hatırlayın. VA is Vs T1 over Tt idi. VA is equal KVS'tir. You remember that. Therefore, Vs, I'm sorry, I couldn't see. Just a moment. So if you look at the current relationship, of course, Vs Is is equal Va Ia, assuming there's no loss. So that means K times Vs times Ia. So Is is equal K times, bu da bir şey. Bu da bir so output is equal K times Vs and output is equal 1 over K times. So this, dikkat edin bakın. Is is equal K times Ia. Şimdi calculating the ripple. Şimdi total period, follow my cursor please. Total period is equal 1 over F, which means T1 plus T2. T1 on time, T2 is off time. T1 is already derived, that one here. And T2 is already derived, that one here. Therefore, T is equal to delta I times L times Vs over Va bracket Vs minus Vl. So when you solve this one, you end up with this equation. This is the period. And delta I, you remember delta I. Bir gidelim geriye. Delta I bulmuştuk burada. Delta I bakın. delta I, either use this one or that one. VA times VS minus VA. So if you put those equations here, T1, T2, and things like this, then you end up with delta I is equal current fluctuation is equal Vs times K times 1 minus K FL. Or in other words, VA times Vs minus VA over FL Vs. Now, what is important here, be careful. There's a question here. How could we reduce the current fluctuation? How could we minimize the current fluctuation? It's obvious. You can increase your frequency. You cannot play with K, since K is actually defines your output voltage. Your desired voltage defines, so you cannot change it. For example, if you have 24 volt battery, and if you need 12 volt, then K is going to be 0.5. So you are going to reduce it half. If you have, for example, 48 volt, which is widely used in communication networks, if you divide 48 volt, if you want to get 12 volt, so you have to divide it by 4, 0.25. K should be 0.25. So you cannot play with K. Then if you cannot play with K, then of course only thing you can play, not only thing, there are two things. One of them is L, the other one, source voltage, is already given. Frequency and inductance. Increasing inductance is necessary to sustain a continuous current mode. It's good, but that means money, cost, and that means increasing L means volume. That means weight. So you cannot increase indefinitely to infinite value. That's why people use high frequency here in order to reduce the size of the passive elements, and also in order to reduce the fluctuations, frequency is increased. For example, 10, 20 kilohertz was used mainly, but now even higher than those are widely used. 100, 500 kilohertz. That, of course, switches should be capable to turn on and off with that frequency. All right. So this is what we have discussed. Now let's concentrate on the capacitor voltage as well. Capacitor current is changing from minimum to maximum, and then from maximum to minimum, and then same pattern. But we can see that, what is Q, by the way? Famous bir denklem vardır. Q is equal to CV. Bir denklem daha vardır. I, ya kalemle yazmıyorum. I is equal dq over dt. So buradan ne anlaşılıyor? dq is equal integral I dt. So this area actually is delta Q. Since this is a time scale, so the area here is the integration of the current. So that is the stored energy. First time he used IL max here, Mohammed Rashid used IL max here. I always use I max and I min, but he prefers I1 and I2. Anyway, now this time is half of the switching frequency, half of this time. Therefore, you can calculate the triangle here. Delta V, bakın geliyorum şuraya. Q eşittir CV değil miydi? Delta V is equal delta Q over C. Şimdi devam ediyoruz. Delta Q neye eşit? Üçgenin alanı. 1 bölü 2 üçgen. The triangle area. Times delta I over 2. Bu delta I over 2'dur şurası. Delta I over 2. Times that one is TS over 2. So that is delta I TS over 8. 2, 4, 6, 2 kere 2, 4, 2 kere 4, 8. 8C. So tekrar ediyorum. Bakın. I repeat. Q equals CV. So delta Q is equal C delta V. İniyoruz buraya. Delta V is equal delta Q over C. That's the equation. Şimdi C dursun. Delta Q neye eşit? This area is delta Q. I prove that one. The I dt is equal delta Q. So the triangle area 1 over 2 times the height is delta I over 2 and the width is TS over 2. Then it's going to obtain delta I times TS over 8L. Bu denklemi tutun aklınızda. Geçiyorum şimdi öbür tarafa. Kitaptan yaptım. Peak to peak capacitor ripple voltage. Şimdi Muhammed bunları bize gönderiyor şeyleri. Slaytlar bize bir yayın evinden geliyor. Ama ben beğenmiyorum, onların üstünde değişiklikler yapıyorum. Tabii bana göre dünyanın en iyi kitaplarından biridir bu. Power Electronics kitabı. One of the best book in the world. And in many universities in United States, everywhere, there are two books that are very popular. One of them is Mohammed Rashid's book. The other one is Professor Rashid's and Professor Mohan's book. Anyway, so using Kirchhoff law, we can write the inductor current. Inductor current is equal to capacitor current plus output current. Okay. And also the IC is delta I over 4. We have already proved that one. So V is equal 1 over C integral I dt, an initial value. So delta VC is VC minus VC time equals 0. So when you get integral of it, delta I 8fc. Bir daha geri döneceğim. Zaten ben buldum burada gördüğünüz gibi. Delta I t 8c. Bir dakika nereye gittik? Uçtuk. Delta I t 8c. Şimdi burada t yerine f koyarsanız delta I 8fc. Buradan delta i'yi yerine koyarsanız if you put delta I, which we already know that, delta vc voltage fluctuation is equal va bracket vs minus va over 8 frequency c, I'm sorry, 8 l c f square vs. Şimdi bu nereden geldi diyeceksiniz. Bakın delta i'yi bir bulalım şurada. Hangisini kullanacağımıza bakarız. Bakın delta I burada. If you take delta I from here, put or that one or this one. Sorry for the cursor. For this one. Delta VC could be obtained VC times K 1 minus K 8 LCF square. That also reflects C, the capacitor size is important in order to reduce the voltage fluctuations, but that is also cost, that is also volume, that is also weight. However, if I manage to increase the frequency, it's the square of the frequency is in the denominator, therefore directly affect to reduce delta VC. So we have already obtained voltage fluctuations, we already obtained current fluctuations, and already obtained all the design values. One final term is that what about the minimum L and minimum C values in order to sustain continuous current mode. These are the minimum values. From those equations, you can easily take this one. Delta, you remember that one here. This is a critical, this is the, as I told you, since I wanted to show you how that equation is obtained. You can see that it directly comes here. So I proved that one. And also the critical value of inductor is equal this value for continuous current operation. And that is also should be necessary to prove. Condition for continuous inductor current and capacitor voltage. That is the heading. Continuous inductor current and capacitor voltage. Critical values. Condition dediği critical values. If IL is the average inductor current, inductor ripple current is delta I is 2IL. Averajın bir üstü bir altı olacağı için iki katı averajın. Delta I. Denklemleri yazarsan şu delta I yerine bunu 2IL yazarsan buradan inductance value can be taken as L is LC, the critical value is 1 minus K R times 2F. So this L should be higher than this. For capacitor values, similar argument. If Vc is the capacitor output voltage, the capacitor ripple voltage is equal to 2 times Va, delta V. Then if you write the equation 2 times here, you can obtain the critical capacitor value is equal 1 minus K, 16 Lf square. In brief summary, now I would like to make a brief summary. I know all the time I talk and your brain now needs to think. What did we learn for this section? We learned about buck converter. Buck converter is widely used in industry to reduce the DC voltage from one level to lower level. Okay, it's buck converter. We already know how to select L value. We already know how to select C value. Of course, the input voltage and output voltage are the starting point. We cannot play with it. Therefore, K is not the one we can play with it, but we have frequency. But while frequency is selected, you have to be careful about the device frequency level. If every device means power electronic switches, MOSFET, for example, or IGBT, insulated gate bipolar transistor. Every device has got rated current, rated voltage. When the current flows, is the maximum current. When the switch is off, the maximum voltage. It resists. Rated voltage and rated current, plus the frequency. There are three things. Of course, frequency means turning on time, turning off time, turning on loss, turning off loss as well. However, when you select the switch, if you select a very sophisticated switch, it becomes very high, very expensive. Therefore, you have to optimize the size as well as the cost in your engineering life. Now we have already learned that there are critical values for continuous current mode, for inductance and the capacitance in order to reduce the fluctuations. Now I bring a problem for you. That is the critical value of the capacitor. We have already proved that one. Şimdi bu problemi yapacaksınız çocuklar. Ama problemi bakın. Şimdi sınavda da ben size problemler falan soruyorum. I ask problems to you. From very early age of your education life, I don't know my Iraqi, Syrian, Lebanon, Egyptian students. I don't know their education system. But in Turkish education system, most of the exams are multiple choice test type. In order to enter the university, you have to become successful those multiple choice test exams. Exams. Yeah, that's right. Examinations. Multiple choice is something quite often reduce the thinking ability of the human mind. Your mind, I'm talking about Turkish students, your mind is concentrated on which one is the correct one between those four selective items, which one is correct. You are optimizing, your brain is optimizing time, your brain is concentrating on which one is correct. But in that case, you're imagining new designs, your of course ability to design a new types, new topologies, and also questioning. You are ready to answer which is already presented to you. For example, I'm asking you, which finger has got the ring? But you are not saying which finger is most suitable to use ring. You are not, this is, you should ask those questions. Or what kind of ring is actually to be most efficient? What kind of ring is more healthier for humankind? That is not asked for test questions. However, let's so you to understand the problem is halfway of the solving the problem. To understand the problem, let's try to understand this problem first. The bug regulator of figure 517. 517 means that's the one. Temizleyeyim bir sayfayı. That's the one. This is the 517. You can see that. That's the buck regulator. So we are now input voltage and we have output voltage. So our main objective is to provide a good output voltage. Bakalım neymiş bizden istenen. The buck regulator of 517 has an input voltage of 12 volt. The required average output voltage is 5 volt. Now it's buck, we are reducing from 12 to 5. And R is 500 ohm. So probably our load is known. And peak-to-peak output ripple voltage is 20 millivolt. You are allowed to maximum ripple voltage 20 millivolt. The switching frequency is 25 kilohertz. Switching frequency is given. If the peak-to-peak ripple current of inductor is limited to 0.8 A, bu da verilmiş. Determine, neleri arıyor? Duty cycle, filter capacitance, filter inductance L, and filter capacitor C, and the critical value L and C. Şimdi problemi anladık. Voltage is going to be reduced from 12 to 5, but resistance is already given. And also current fluctuation and voltage fluctuation is given. The maximum values are given. So delta I and delta could be calculated. Now, voltage, burada da şeyler var. 12 volt, delta V is 20 millivolt, delta I is smaller than 0.8 A, frequency 25 kilohertz, and the output is 5 volt. Şimdi bir kere K hemen buradan bulunur. K is equal VA, V output over input is 5 over 12 is 0.41. From equation 559, where inductance equation, o denklemi bulayım size. Buyurun. 559. Delta I is equal VA, VS minus VA, F, frequency L, VS, sorry. Yes, VS. That's the equation. Gidiyorum. Değerleri yerine koymuş. 12 volt giriş, input. 5 volt output. 5 volt output. Burada 12 volt giriş. Ondan sonra 0.8 is delta I. Ondan sonra frequency 25,000. Buradan inductance is obtained 145, I'm sorry for Turkish, 145.8 microhenry. And also C zerde filtre kapasitör istiyordu. O da 0.8 bölü filtre kapasitör de 561. Onu da göstereyim. Denklemi bir daha. Evet, 561 burada gördüğünüz gibi. Delta I over 8FC. Simple. Delta I is already given. Frequency is already given. So delta V is already given. So we are going to calculate C. C is equal to 0.8 is delta I. Ondan sonra zaten 8 vardı. 25.000 burada frekans var. Bir de delta V'de 20 milivolt verilmiş. Misler gibi. You can find 200 microfarad da burada buluyorsunuz. Şimdi D şıkkı LC value equation'ı olduğu gibi uygulamış. Bakın R orada girdi işin içine. LC value, you can obtain LC here and you can also obtain C critical. L critical is 583 and C critical 0.4 microfarad. Şimdi ben bir geri döneceğim. 583 milihenry. Biz bu değerden bakın biz microhenry bulduğumuza göre biz yani critical value'dan daha yukarıdayız. Değerimiz daha küçük yani. Orada yanlış yorumlamayalım, olur mu? Bakın 583 milihenry C de 0,4 mikrofarad. Geliyorum buraya. Biz 200 mikrofaradız. Burada kafam biraz karıştı benim çocuklar. 240 145 microhenry 0.1 milihenry'dir. Endüktansımız yorumlamamış şey. Neyse bu kalsın bakalım. Ama burada yani 0,4 microfarad critical value bizim bulduğumuz zaten 200 microfarad. Bunun çok üzerinde kapasite. Acaba burada bir işlem hatası mı yaptı? Bir dakika bir kontrol edeceğim çocuklar. Tabii sizin bilmediğiniz bir şey var. You don't know that. When the book first published, there are a lot of tiny little errors in it, and those professors various parts of the world send a letter to the lecturer or writer, and then they correct it. But this one is a fourth version, so I don't think there is an error here. Ama bir çarpıp böleceğim şimdi. 12 minus 5 7 çarpı 5 eşittir bölü 0.8 bölü 25 bölü 12 12 equal to 0.14 Millihenry ya. Çocuklar, can you make this calculation again? I obtain millihenry, not microhenry. Allah Allah ya. Who is making calculations? I obtained 145.83.145 millihenry. Hiç kimse hesap yapmıyor mu? Who is calculating? We have 18 students in our classroom. Bravo size. Bir daha yapacağım. Yine nerede buluyorum? 35. 35. Divided by 0.8. Divided by 25. Divided by 12. Equal 0.145. If you divide by 1000, then it's going to be this one is 0.145 Henry. If you divide by 1000, it becomes millihenry. Ne biçim renk Allah aşkına ya. Burada hiç güzel görünmüyor. Biri bir şey yazdı, Allah razı olsun. Tamam Muhammed Sadık. Thank you. Bu Henry. Minus 4 Henry. If you multiply with, that's right. So that's the 10 to power minus 4 Henry. So that one is 0.1. .1 millihenry. Ha 145 microhenry diyor. Doğru o zaman ya. Bu millihenry ise if my calculation is 0.1 millihenry, so if you multiply with 145 microhenry is correct. That's right. Bir de şunu kontrol edeyim bakayım ya. Yanlış yaptım. Baştan. Vallahi ben bulamıyorum bu sayıyı ya. Bir daha yapacağım. Evet, hesap doğru. Peki, çocuklar, yani bunun benzeri problemler var. Düşünebilirsiniz üzerinde. Ben de galiba geçen sene sınavda bir başka problem icat edip sormuştum size. Şimdi şimdi next topic is DC to DC boost converter. Next week ne güne geliyor? Bir dakika. Next week 25'i. Tamam. İkisi 3 hafta kaldı ha. Şimdi 25'inde ders yapacağız. We are going to make a course and second and then Mayıs'ın bir ay sonra 9th of, so we have 3 weeks, but we are completing the DC to DC converters. Next week we can complete the boost converter and also boost converter equations I already put. Bakayım problemde koydum mu? Evet. Problemi de koymuşum. Sonra buck boost converter. Hızla onu da yaparız önümüzdeki hafta. Equations are already there. Buck boost converter. Evet, evet. Şimdi çocuklar bu Çuk converter yani Profesör Slobodan Çuk şimdi Amerika'da yaşıyor. E, Yugoslav. Bu devreyi o buldu, icat etti. Ondan sonra bir de sepik converter var. Biz mesela sepik converter üzerine proje falan yaptık. Yani bunun kardeşidir o da. Ve yani uyguladık da sanayide yeni. Ama bunu kapsamayacağım ben. Bunları anlatmayacağım. Bakayım bu konu burada Chu converter'la bitiyor. Ha, sepik de var. Ama bunu anlatacağım çocuklar. Bu çünkü bu yani peynir ekmek gibi kullanılan bir devre. Power factor corrected. Buna boost rectifier da diyorlar. Bunu anlatacağım. Bu yani önemli bir konu. Hemen de anlayacaksınız. You are going to understand that one. We already spent too many times on the converters now. That's the last topic is going to be three-phase rectifier fed boost converter. That's the one. Boost converter. This is what we are going to discuss next week. The modeling. These are theoretical. I have no time to discuss that one since we have to see also the inverters as well. Next week we can talk. We can complete the DC to DC converters next week. Okay. Now I'm going to take the attendance list. The last person is right. Omar, Muiz, Muhammed, Sadık, Muayyat Abusen, Meryem El Otari, Mahmut Ramadan, Kasım Doğukan, Hüseyin Maher, Erdem Keleş, Baran Edip, Saatçıoğlu Ali Ömer, Aysa, Ahmet Orabi, Adil Bayraktar, Abdurrahman Efe Kork ve Abdülbari Abdülbaset Abdali. Hepiniz kaydoldunuz. Gene de gitmeyin. Don't leave. I would like to stick to my attendance list. Power electronics. Power electronics. Year 2023. Attendance. Before you leave, I would like to say something about Ramadan. Now it's coming to end. I don't know how many of you are fasting. So yani Allah kabul etsin şeylerinizi, dualarınızı. Hepinizin bayramını kutluyorum. I wish you have a very nice festival, let's say, holiday. All the best. Thank you. Bye-bye.